Hi everyone, and welcome to this sixth section of CS-188. So we are going back at this problem involving treasure hunting, and today we are going to delve deeper into this as we are going to learn more about Q-learning and probabilities. So I just filled out the answers that we gave in last week's video for A to C. So here Miss Pacman is walking around and she can perfectly execute her actions, so there is no randomness. If she decides to go somewhere, she goes there. So we have these optimal values that we get in this context, and also the optimal policy in purple here. So now we call this policy pi 0. And the thing is that if we are trying to learn something about our environment, following a given policy is not the best way to gain information, because basically we are just going to exploiting a policy that we think is optimal. But in fact, if we have imperfect information, we'll need to explore the environment to make sure that this is indeed an optimal policy. And so here we'll introduce the concept of epsilon greedy policies. And here, so we have pi epsilon. At each state, we choose with probability 1 minus epsilon to follow pi 0. And with the probability epsilon, we randomize completely. So that will enable us to have the opportunity to deviate from a given policy, in this case pi 0, and explore more about our environment. So in question D, which is the first new question of this week, we are asked to write down what the Bellman equation looks like for a policy pi AS that is stochastic. So when we have a stochastic policy, in fact, instead of associating an action A to a certain state, it will take a state and associate a probability distribution over the actions, which is lowercase pi. So maybe I will write down a bit more clearly here. This is a probability distribution over actions available in state S. And so typically these can have the following shape. So these are the different actions that we can undertake, and the pi here of S action can be something completely uniform. So this is a fully randomized distribution, or can be deterministic. So in this case, the probability distribution will be 0 everywhere except in a certain action. And here, in fact, we have something that's in between. So we have a certain action that was given by pi 0. So this is pi 0 of A. So this one will be given more importance. But then we'll have a certain probability of ending up in other actions. So that's our epsilon. And this would be pi epsilon of SA. So here, this is epsilon greedy. And the way I have written it, it needs to be normalized. So generally what we do to do that, we divide by the sum over the actions, the normalized policy. and here we get then pi, which sums to 1. So that's what we are concerned with in this problem, and therefore if we take a look at our expecting max and we try to write down our value function based on that, well, we'll sum over two outcomes. So the first one will be sum over the actions that we choose, and for each action we have a certain probability distribution of ending up in there. So that's our policy, and this choice is independent from the randomness that belongs to the environment, which is now entailed in this second sum, which is the sum now over the successors of where we can end up if we choose the action A in state S. And the reason why we simply multiply the two is that here these are two independent random variables. So if you materialize this with chance nodes, you could say you have S, then you have a chance node, you'll have the different A's, and then there you will get another chance node. This is with the probability distribution of t, so the transition function, and here this is the policy that we use to understand how the chance node works. So the key point is that these two things here are independent. This is why we can have this product here. Okay, so that's the answer for the first question. Now, E. So we are asked which of the following statements are true. So let's write down the statements. The first one is that the optimal policy can be higher in value than the epsilon greedy policy. The second one is that they can be equal in value. And the third one is that the optimal policy is lower or equal in value to the epsilon greedy policy. And here, so the answer is that pi 0 by definition is optimal. Therefore, the statement that's always true is I. Okay, so then we really start dealing with reinforcement learning. So we assume we see various episodes, and that will inform the policy that Miss Pacman is going to choose. So we have these different episodes, and here we're also informed that in fact one of the fire pits doesn't follow the same dynamics as before. So as you can see here, we're able to move in the sequence of episodes from 0, 0, that is to say the bottom left corner of the grid, to the road that's above that. So that used to be a fire pit, and here in fact we are still able to move north. So something has changed. Then we have the second episode. So I'm just going to write them down and then explain in a bit more detail what is represented in these episodes. Because in fact these quantities here stand for state, action, and successor state. But there's also the rewards that are present in the middle of all of this. So let's just make sure that everything makes sense here. So these here are states. This is an action, and this is a reward. Okay? And we remember that when we do Q learning, so we take Q of, so when we update our Q function for a state and action that we observe, we only take 1 minus alpha times our previous Q function, plus alpha times a sample, and the sample is always the reward we got, plus gamma times the max over the actions available in the successor that we obtained of the Q values in the successor. So that's our definition of a sample here in Q-learning. So here we assume that we initialize at 0. And sorry, that's a k here. So we initialize with a 0 Q function for all states and actions. And now we run the Q-learning algorithm. So let's first take a look into what happens, which state will be updated. So here, for example, we'll have the state 0, 2. And the action that we observe in this state is X, so that will be a state action pair that will have an update thanks to Q-learning. So in the first episode we update this, and we have Q1 of this state and action pair is 1 minus alpha times Q0 of that state action pair, which was 0, plus alpha times the sample, and the sample is this reward, which was 128, plus gamma times a max over nothing. So here, in fact, if we were to write that, we get minus infinity. So let's just not write this max, because basically here the successor is a terminal state. So let's write nothing and stop there. Okay, so now we have our update, and we assume that the learning rate is 1. So the first update gives a Q value of 128. The second one will be a bit different now, because the sample we observe is exactly the same, but the previous Q value has changed. Here we have Q1, so 128, but because we assume that alpha is 1, this is 0, and so we still get 128. So basically the only thing that matters now is what we see in the second episode, because the learning rate is 1, so basically we forget everything that we knew before when we get a new sample. So we can do the same thing for the other state action pairs. So we can take a look at 0, 1 north, for example. So we started with a 0 plus alpha times a sample, which in this case will be 0, because there is 0 rewards, plus gamma times the maximum over the successor that we got. And the successor after 0, 1 here is north. Is going to be 0, 2. That's the state we get after 0, 1, this chain. So we see here we have 0, 1, choose the action north, we end up in 0, 2. So that's what we inject in our sample. So here we initialize the values with zeros, so that doesn't change anything. So at the first step we get 0, but at the second one, because now we have a Q1 which has changed and is non-zero, we get alpha times gamma times 128, and this time we get 64. Okay, so now let's take a look at what else gets updated. So we have an update for 1, 1 and X, and in this case, we have 1 minus alpha times Q0 in that state action pair, plus alpha times a sample, and this sample here is minus 64 plus nothing, because we end up in a terminal state after that. therefore here alpha being 1, we get minus 64. The final update we get is for the state action pair 01E. So as always, we have 1 minus alpha, the initial value for this state action pair, and this is 0, plus alpha times the sample we get here. So after 01 east, we end up in 1, 1. So we get 0 reward plus gamma times the max over actions of Q1 here of 1, 1 action. And here, so we got a minus 64, but we also had a bunch of zeros that corresponded to the other actions. So this max here is going to be 0, and therefore we get 0. So that's it. Now, in question G, we are asked if in most cases a learning rate of 1 will result in a failure to converge. And this is completely true because, as you can see here, basically each time we get an update, we forget everything about the Q function we obtained so far. So the reason why this works is that there is no randomness in the transitions. And therefore, one sample is enough. There is no need to compute a running average here. Okay, so now in the last question, basically we incorporate the new knowledge we have about this environment and the new rules. And because we've not observed state action pairs for all the states and all the actions available here, we are going, if we don't have any knowledge from our episodes here, to fall back to the knowledge we had in the first question of the problem. So basically that means that the only thing that changes is that we learn that now we can transition as follows, and therefore if we compute our values, well, this will have not changed, and because we assume we still have the dynamics of the old problem, we still get these values here. However, this value now will change because we discover it's better to go up. Here, we also discover that it's better to go up, so the value will be 32. Then the value here will become 16, and the optimal policy is now like this, we're indifferent in A, and that's how we should behave now. Okay, so now the mini power pellets. So now we assume that Pac-Man can carry around power pellets, but they look just like regular dots. And they give him a better shot at winning against the ghosts, but still there is no guarantee. So here, let's just, before we compute this marginal probability that Pac-Man does win, recap the two random variables we are considering, S and W, and their outcomes. So S can be plus S, a mini pellet with a probability of 5 over 20. That is to say 0.25. And it could also therefore be a regular dot with a probability of 0.75, unfortunately for Pac-Man. Now for the win variable, so we are being told that if Pac-Man has just eaten a mini pellet, it has a chance of 0.7 of winning, which means that it could lose with a probability of 0.3. And now if we take a normal dot, well, Pac-Man will only have a 20% chance of winning. So much worse odds in this case. Okay, so how do we compute this marginal? Well, let's just say that, whoops, this is the probability that we win is just the sum of the probability that we win and we've taken a mini pellet, plus the probability that we win and we've taken a regular dot. Okay, these two elements, these two events, plus S and minus S, are disjoint. So here we're just using the rule of the probability of the union of two disjoint events. And now let's just rewrite the joint probability as a function of the conditional times the marginal. And the same thing for the second element in the sum here. So let me just write this. So you've probably finished this question, but if you want to be methodical about it, write down everything, and here be careful about which rules you use. So here we just use the definition of the joint as a function of the conditional probability, which is so this product here that we get. And now let's just substitute by the values we have numerically. So this is 0.7 times 0.25 plus 0.2 times 0.75. And if we compute that, we get 0.325. Okay, so that's just the marginal probability of winning, and therefore that means also that the marginal probability of losing is 1 minus the 0.325 that we just got. That is to say, pretty high. Oh, sorry, that's a 6. Okay, so in the second question, we are being told that Pac-Man just won. So that's some information we have about the state of the world, and we are going to leverage this information to infer the probability that Pac-Man did win, having taken a pallet. And so what we use here to compute this conditional expectation is just Bayes' rule. So we can go back to the definition of this conditional probability as the joint divided by the marginal. Now we can rewrite the join, but with a different conditioning. So we just swapped the variables. And we re-inject the values that we had before. So for this one we have 0.7. For this one we have 0.25. And we divide that by the marginal we just computed, 0.325, which gives us about 0.538. Okay. Okay, so in the third question, we add two random variables, B and M, so the breadth of Pac-Man and whether the ghost is mean or nice. And as we have more information about the world, we can make better informed decisions. So first of all, here we are given this big joint table, and as you will notice, there is only plus M that's taken into account here. So if you see that this table doesn't sum to 1, it's completely fine. It's just a partial probability table. It will be enough, though, to compute the marginal probability that we encounter mean ghost and Pac-Man has bad breath. So here we are going to use the additive property of the probability with respect to disjoint elements. So we have the state of the S variable that can be plus S or minus S, so we are going to sum over these two, and the state of the W variable, which can be plus W or minus W. So we are going to sum all of these occurrences of plus M and plus B, and therefore we can look up on our table everywhere we see plus M plus B. So here we have a plus M plus B, so we are going to take this value of 0, 0, 6 into account. Here we have plus M plus B, we need to add it to our sum, plus M plus B. So we just look up the table and we gather all the occurrences of plus M and plus B. And we're done. There's no other occurrence. And if we do this quick calculation here, we find 0.25. Okay, so now we are asked to compute a conditional probability. So Pac-Man knows he has bad breath, so we know that we are in plus B, and we are asked to compute the conditional probability of winning if we meet a ghost and we have bad breath. So here what we're going to do is go back to the definition of the conditional probability as a function of the join. So we just write the join over these three variables. And we look up in our table where we get plus W plus M plus B. So that happens here. So we have 0.06, and so plus W plus M plus B also happens here, and that's where we get our 0.015. Now we are going to divide this by the probability we just computed, so 0.25, and this is 0.3. Okay, so that's how we can use a join table in order to extract a certain marginal, and then in order to compute a conditional probability.